My name is Megha Mishra, and today I will be talking about the 5th Physics 2211 lab. I chose a falling slinky as my topic. The overall purpose of this lab is to observe and understand the unique motion of a slinky that is stretched and then is dropped from rest, and to compare it to predicted results generated from a computational model. To preview the results, what we end up finding is that predicted motion closely relates to the observed motion, as the computational model accounts for all the main forces that are acting on the slinky. The main physics principles that underlie this lab is Newton's second law, which concerns the system and the surroundings, and states that a force that acts on the system from the surroundings results in changes with momentum. I've included a general formula which states that the net force is equal to the change in momentum over the change in time. From here, it's possible to calculate both the velocity update and position update formulas, which will be used in the GlowScript code. The net force is the sum of all forces acting on the object. In this lab, the net force is a non-zero value, and thus velocity is not constant. This is due to the presence of drag, gravitational force, and a force I will be calling the Slinky force. Gravity is the acceleration of a falling object at or near Earth's surface, and is represented as being negative mg. Drag is a force that acts opposite to the relative motion of a moving object, and has a magnitude that is proportional to an object's speed squared. And finally, the Slinky's force is a type of tension that refers to the force the Slinky's entire body is exerting on the bottom portion of itself, due to how the Slinky is initially stretched out. This force is the reason that the object remains stationary until the entire length of the Slinky has fallen to meet the bottom portion. The observational data was obtained from a video of a Slinky being dropped from rest. In this scenario, the system is the Slinky and the surroundings are everything else. I used Tracker to track the Slinky's center of mass frame by frame. Tracker was also able to provide the initial conditions. The pink lines here in the picture represent the coordinate plane that was used. From here, the initial position of the Slinky was calculated as being 1.582, 3.165, and 0 meters. Since the Slinky is being dropped from rest, we know that the initial velocity is simply 000 meters per second, and I tracked the motion beginning at time t equals 0. The data obtained from Tracker can be seen represented in the form of position versus time graphs on the right portion of the photo. We're looking at the second graph specifically because we're observing the Slinky's motion in the negative y direction. Next, I obtained predicted data through creating a computational model in GlowScript that was made through code modified from the starter code provided to us for Lab 2. The mass of the Slinky is 0.25 kilograms, and the initial conditions for position and velocity were obtained from Tracker as previously explained. The initial time is at 0, and the gravitational force g is a constant value of 9.8 meters per second squared. The proportionality constant was calculated as being 2.6. The first while loop on the left represents the period of time where the bottom of the Slinky is stationary. The forces acting on the Slinky are first defined. These forces are the gravitational force and the Slinky force, which are equal and opposite to one another, and thus the net force is 0. The momentum principle is then applied, updating the velocity and position, but as the net force is constant, the velocity is constant, and thus position does not change, which helps explain why the Slinky is stationary for this portion. The second while loop on the right represents the period of time after the entire Slinky begins to move. Here, the forces acting on the Slinky are different, being drag and the force of gravity, which means that the net force is no longer 0. The momentum principle is then similarly applied, updating velocity and position for the falling Slinky. Here is the computational model generated by the code. This represents our predicted data. We can then conclude this lab by looking at a comparison of the predicted versus observed motion. As we can see in the picture on the left, the computational model closely mirrors the data gathered through Tracker. This shows us that by accounting for all potential forces that would be acting on the Slinky, we are able to actually create a relatively accurate prediction for motion in the y direction of the falling Slinky. There are some minor deviations that occur, particularly after the Slinky starts to fall. This could be due to inaccuracies in tracking the center of mass via Tracker. As this was an individually chosen lab, there are no set why or what's next questions to further examine, but I think going forward it might be good to try analyzing the Slinky in both top and bottom parts separately, as opposed to the entire thing using the center of mass. This might also help the predicted versus observed differences to be even smaller than they already are. Thank you.